Hello, my name is Raul Cornejo and this is LabActivity number 8 for class EEE3303 Lab. We begin with part 1, which is based on this transistor circuit. Here is shows and values for R1 is 22 kilo ohm, R2 is 11 kilo ohm. The resistor for a collector is 1.5 kilo ohm. Emitter resistor is 1.1 kilo ohm. The DC power supply was chosen to be 9 volts. And so with these resistor values, I get the voltage reading of 2.76 volts in the resistor, 2.16 volts in the emitter resistor, 2.83 volts in the collector resistor, and the base current of 0.01 milliamps. The current with this branch right here is measured out to be 0.25 milliamps, and the current on the collector is measured to be 1.91 milliamps. And here are the results for a multi-sim simulation. You can see this is 6 is right there, 2 is right there with 3 volts, this is 4, corresponds to 2.21. And here we have the circuit for this branch right here. So around 0.263 milliamps. Yeah, the base current is much smaller, and the collector current is around 2.003 milliamps. So the closing value. Here's the circuit itself. Got all the resistors lined up for the collector. Here's the R1. Here's the transistor, the emitter, and then this is just going to ground IR2, voltage. So the measure value of VR2, the transistor connected, is 2.76 volts. The measure value of resistor 2, the transistor remove, the transistor remove is voltage of 3.04 volts. And it's because the circuit branches of the resistor collector and the resistor in the emitter are cut off. So this only remaining circuit is just a branch of R1, which is 222 kilo ohm, and R2 11 kilo ohm in a series, as you can see right there. And these are just cut off. So the total resistance 32 kilo ohm, and still voltage. The total voltage is still 9 volts. And then the total current is found to be 0.272 milliamps. So the theoretical value of the voltage drop should be around 3 volts, 2.992, which is close to what the multi-sim was measured. So in here, C, when there's no resistor in there, basically 0 ohms, the collector current is 1.93 milliamps, and the collector emitter junction is 6.31 volts. 100 ohm resistor in the collector is going to be a current of 1.93 milliamps, and the collector emitter junction is going to be 6.1 volts. So in here I just wrote that the addition of a voltage divider is right here. Helps the bias of the transistor stay constant while also providing thermal stability. The voltage divider bias circuit functions properly when the current through the voltage divider, I2, this branch right here, is higher than the base current going through here. Activity 2, use similar, basically almost the same electronic components as before, with only the addition of a capacitor 1 is 0.47 microfarads and capacitor 2 is 0.1 microfarads, and also a sine wave input signal of 1 volt peak to peak. And here is the circuit itself built. Input frequency of 100 hertz. You can see a voltage gain of 0.546. Frequency of 500 hertz is a voltage input of 1.997. Input frequency of 1 kilohertz, a voltage gain of 3.749. At 5 kilohertz input sine wave signal is a voltage gain of 7.373. And the 15 kilohertz input frequency is a voltage gain of 8.818. And the input frequency of 20 kilohertz gives off a voltage gain of 10.87. So the mid frequency seems to be between 1 kilohertz and 5 kilohertz, possibly 3 kilohertz is the frequency range when the voltage gain is half the value of BCC. The waves are clear and more defined in the circuit of a combination bias of sub-bias and the voltage divider. There is less distortion visible in the output signal when compared to circuits previously done on other experiments. So activity number 8, part 3. Some very similar circuit to part 2, with differences that the emitter capacitor removed and C1, capacitor 1 is changed to 0.003 microfarads. Everything else, the resistor values all remain the same, and there's still a wave input signal of 1 volt peak to peak. There's a circuit, and I got it here as well. This was the last one I just did. Input frequency 100 Hz provides a voltage gain of 0.0806, small value. Frequency 500 Hz, voltage gain of 0.216. Input frequency of 1 kHz provides a voltage gain of 0.414. Input frequency of 5 kHz provides a voltage gain of 1.777. Input frequency of 10 kHz provides a voltage gain of 3.563. Input frequency of 15 kHz provides a voltage gain of 4.966. And finally, input frequency of 20 kHz provides a voltage gain of 6.114. Mid frequency seems to be around 10 kHz in this circuit, and also the output does not reach the power supply value of DC. And that's it for this experiment. Thank you for watching.